Sorry.
Okay. So it is a very great pleasure for me to be able to host Charles Brown here today. I think this feels a little bit extra festive, frankly, being back in room 104 for the first time in I forget how long. So yeah, have this a little bit celebratory. Did things work? Oh yeah, sorry. I'm not used to doing that. Thank you. Yeah, just project, right? Right. But there's people not here. Okay, so Charles is currently coming to us from Berkeley in the group of Dan Stanford-Kern, where he's been working on optical lattices. He'll be discussing with you. He's had a really amazing track record, really distinguishing himself as a bit of a virtuoso experimentalist, I have to say. Particularly the work that he did for his PhD in the group of Jack Harris, which is, I think, well known to those of us who've been around the department for a long time. His PhD work was studying magnetically levitated drops of superfluid helium, believe it or not, and looking at the optomechanics of that system and various other things, which is an amazing hybrid physical system looked at, frankly, as far as I'm concerned. He's got a lot of other things that he's involved in that are really impressive. He's a co-founder and co-leader of the Black in Physics Week, which is dedicated to celebrating the historical contributions of Black physicists. And he's been involved quite a bit in that community. I don't know to what extent you were going to talk about that today, but we are very happy to have him here, at least I am, and looking forward to hearing what you have to say about all the stuff going on at Berkeley lately.
Thanks.
So, thank you.
Yes, thank you for the introduction. I'm very happy to be here. Happy to be leading the charge and getting the talking series going back in this room. I won't be saying anything about Black in Physics Week today, but please do check it out. It's a very important initiative that I'm heading up. Today, I'm going to be telling you about our recent experiments looking at a probe of band structure singularities using a lattice-trapped quantum gas. So again, I'm Charles Brown, coming from Berkeley, as Kevin said. I wanted to first point out my experimental and theoretical colleagues. First, these two students, Xiaowen and Malte, these are two young grad students that I have the privilege of working with. This was a senior grad student, recently turned postdoc, who's now in industry, doing some very exciting science, applying optical techniques used in our AMO lab to biological systems. And of course, my postdoc advisor, Dan Stanford-Kern. And on the theoretical side, grad student Alex, a postdoc Vlad, who is now starting a faculty job at Carnegie Mellon. So congrats to him, and Joel Moore, condensed matter theorist in the department. And of course, these very important groups that fund our work and allow us to do the science that we do. Okay, so I mentioned that I was going to tell you about this probe of band structure singularities. In order to do that, I need to talk to you about quantum simulation. And it turns out that the important way that I think about the system that I work on is as a quantum simulator. So what is quantum simulation? Here's my definition of it. Quantum simulation is mimicking quantum systems for the purpose of understanding their states, phases, and dynamics. Okay? And so I would say that in quantum simulation work, you might be thinking about Hamiltonians that describe your system. A Hamiltonian that has a general form like this, where this Hamiltonian has some kinetic energy part, some potential energy part, and some interaction part. Sometimes this Hamiltonian can be simple. Sometimes it can be very complicated, especially if this part is complicated. And so it could be useful to either use a device or a computer or something of that nature, or an analog system that you build in a lab in order to solve this Hamiltonian. Okay? And so I like to think of quantum simulation as having sort of two forms, that is digital simulation and analog simulation. I'm on the analog side, but I want to pay homage to the work that's happening on the digital side. It's an important piece of this puzzle. And so digital simulation requires some sort of quantum computer device, right? Something like what Google has, or IBM, or Honeywell, or IonQ, either a trapped ion device or a superconducting qubit device or something like this, where you can initialize some state, you perform a quantum algorithm, which is really implementing qubit state transformations, and then you measure it. This is in contrast to analog simulation, again, what I do, where you build a physical system in the lab and you do measurements of it. And this can take various forms. The way that I build a quantum simulator is by looking at cold atoms in lattices. And that's what I'm going to talk to you about today. But there are other systems. One I've already mentioned, this trapped ion chain system, which there's sort of a bifurcation now between quantum computing devices built with them and then stuff happening on the academic side in the lab that's separate. But also these other systems where you can use arrays of optical tweezers to trap atoms in some highly excited state and build qubits from them. Right, this is an interesting platform for trying to do analog quantum simulation. Or completely photonic systems where you can do quantum simulation type experiments using a series of photons and beam splitters and just all optical components on the table. Okay. Now, when I think about quantum simulation, I would say that there are two problem types that have been addressed. And that is time-dependent problems and ground state problems. So when I say time-dependent problems, I mean problems related to equilibration and thermalization, for example. Where in this experiment, experimenters they take a lattice system and they sort of move their atoms over to one side of it, release the atoms, let them diffuse through the system and sort of look at in their different lattice sites, how the density of atoms change as a function of time. Something separate you can do that's very interesting is look at dynamical phase transitions, where in this example, experimenters take a superfluid and they transition the system through a phase transition, where when they go through that phase transition, excitations in the form of vortices with quantized angular momentum pop up. Okay. Or you can look at kick systems, flow case systems, where you add a time-dependent energy into your system, which really gives you a whole variety or access to a variety of physics. Okay, so that's sort of what I think about when I think of time-dependent quantum simulation problems. There are ground state problems as well, where you can start to look at quantum magnetism. So here, this is a clip from Wasim Baker's group at Princeton, where he's using a quantum gas microscope. This is a single site resolution image of cold atoms in a lattice, where you can start to see site-to-site, you have site-to-site resolution of the atoms in the lattice, and you can see sort of spin up and spin down, and that's what the different blue and white squares are, right? So being able to see magnetic ordering in these cold atom systems. As a sort of extension of that, maybe you want to look at quantum spin liquids, where you use these tweezer arrays that I mentioned to make sort of complicated lattice arrangements. This is called a Ruby lattice, but this gives you access to studying a very desirable state as an experimentalist, is quantum spin liquid, which can sort of be thought of as a quantum superposition of a bunch of different ordered spin states that I guess when you go to measure it, you see that even at zero temperature, you sort of lose this ordering. Or you can try to look at physics like superconductivity in these cold atom systems. So again, these are sort of the different ways that I see quantum simulation can go. And I wanted to make a point that it's not just for condensed matter. So even though that's my focus, right? I'm an AMO physicist that thinks a lot about condensed matter problems. I would say that quantum simulation is also very interesting for high energy physics. So here I took a clip from Monica Eidelsberger's thesis, where you can see an image of a square array of atoms. So the gray circles or spheres, those are the atoms. And you see they have a square geometry. And there's a little yellow image of circulation with some red arrow coming out. This is a depiction of a synthetic magnetic field that you can generate in these cold atom systems. And so this is an example of what people call synthetic gauge fields. And this is really nice because high energy physics tells us that gauge fields are ubiquitous in nature. For electromagnetism, that gauge field is the photon. For the strong force, it's the gluon. For the weak force, it's the W and Z particles. And so I think that certainly myself and lots of other cold atom people think that this is a very interesting future for a cold atom experiment, where by using a couple different techniques, maybe lattice shaking or some other thing called laser assisted tunneling, you can generate these synthetic gauge fields. And if you can make them time dependent, right, then you start to move into what you might call a dynamical gauge field. And then that's really interesting because any kind of quantum field theory that you might be able to address with a cold atom system needs to be dynamical. Okay, and so I just wanted to point out, I think this is a very, very exciting potential future for cold atom physics. But I want to look at condensed matter physics problems, and so let me tell you why. And that's because there are many exciting questions related to exotic superconductivity and magnetism, quantum Hall effects, and generally topological matter. I would say that compared to solid state systems, we have a number of important advantages. That is, we have controllable defects. We can essentially make perfect lattices, or we can put disorder in them in different ways that we want to. We have long-lived quantum coherence. We can prepare many identical copies of our system. And we have a nice ability to study lots of different kinds of out of equilibrium physics. Okay, and so I wanted to make this point here that I think we can provide great insight into the behavior of solid materials that have crystalline lattice structures. And here I'm showing you an image from the lab, what I would call a diffraction image from a honeycomb lattice, where we can take our Bose-Einstein condensate, which very much behaves wave-like. And similar to how a crystallographer can do diffraction measurements, we can diffract the matter wave of a Bose-Einstein condensate from an optical lattice and learn about how these particles behave in this lattice system. Okay, so I'm talking a lot about crystal lattices. I'm telling you that this quantum simulator can teach you something about real crystals. Let me tell you about crystals. So I would say that a crystalline lattice, this is one definition, is a periodic set of points that has some set of symmetries. One such lattice is a square lattice, which I already showed a couple slides ago. It has translation symmetry, so I can draw a box, say around this circle here, and I can translate that box up and down, left and right, and I can completely span the lattice. Okay? I can also rotate this image by 90 degrees, and the image looks the same. So it has a rotation symmetry. It also has translation symmetry. Here's a triangular lattice. It has translation symmetry again. That's a different rotation symmetry. Here's a cogomate lattice. Again, translation symmetry, different rotation symmetry. There are many other lattices, but the point that I want to make here is that lattices have band structure. Okay, what is band structure? Well, it's the energy of a particle in that lattice versus the momentum of the particle in that lattice. Okay, and there are two sort of extremums to consider when you're thinking about what band structure is and sort of what it means for your system. So I can look at these two cases where this quantity I'm calling V lat, this is the depth of the lattice. This is how strongly particles are confined to these black points. When that is 0 versus when it's non-zero. So here's a case where the particles actually fill the lattice. Here's when they do not. When the particles do not fill the lattice, you have the sort of relationship between energy and momentum that you expect. The variation in energy with momentum is quadratic, right? Like p squared over 2m. And so you see these parabola. However, when you turn on the lattice, you actually create confinement at these black points. You see that you open up these gaps in the white, where the particles can only have energies that fall within these colorful bands here, the green, the blue, or the red. And they cannot have energies that are in the white regions. Okay? So a solid's band structure describes the allowable energy levels for electrons in a crystal lattice. And it turns out that band structure explains quite a few material properties. For example, electrical resistivity and optical absorption. Okay? It's a useful tool to describe the state of your system using these block wave functions. And I only want to sort of bring this up because later I'm going to talk about these weird cases where this function, psi, this is a block wave function that describes your state, becomes ill-defined. And it turns out that it becomes ill-defined because there's some interesting topological property of the system. Okay, so these block wave functions, they look like this. There are some function u multiplied by a phase, e to the I q dot r, where this function u so my battery died. That's okay. This function u has this cell periodic feature. So if you look at the function u at some position r, and you look at it at some position r plus a lattice vector away, this is the spacing between two adjacent lattice points, the function is the same. Okay, so I mentioned to you that band structure explains material properties, but it doesn't explain all of them. It turns out that the geometry and topology of the state space where the wave functions live that describe your state also is important for material properties. For example, the geometry and topology of state space is related to, for example, quantum Hall effects or orbital magnetism or topological insulators, where instead of just looking at the block wave function psi, you need to think about this rather mathematical term called the Berry connection, which tells you about how vectors are connected in space.
Try not to distract too much, sorry. Distraction.
Thank you, thank you.
Hope it works.
Okay, and so that is what I want to tell you about crystal lattices and the importance of their energy bands and the importance of the geometry and topology of the state space where the wave function is used to describe the system live. Okay, and so that's sort of one component of this quantum simulator, the lattice, at least some concepts about the lattice. But in order to study this physics, we make Bose-Einstein condensates, as already mentioned. So let me make a couple general comments about bosons and Bose-Einstein condensation. So what's really relevant for me as an experimentalist that makes Bose-Einstein condensates is putting these particles in harmonic traps, like this one here. So what I'm showing is the difference between how bosons behave versus fermions in a harmonic potential, right? So this is a quantum harmonic oscillator that has these energy levels that are labeled by n equals 0, 1, 2, 3, et cetera. That's what these different lines are, right? And so even at zero temperature, the important difference between bosons and fermions is that bosons are totally fine with occupying this lowest energy level, whereas fermions are not, given the Pauli exclusion principle. They stack themselves up across these energy levels up to the Fermi energy, right? But this behavior, where multiple bosons are able to occupy the same energy level, this is what allows us to make Bose-Einstein condensates. And so in our lab, we use the bosonic isotope, rubidium-87, to make these condensates. So what is it? Well, a Bose-Einstein condensate, I would say, is an exotic state of matter, very interesting one, where its wave-like nature becomes really important. So the de Broglie wavelength describes the wave-like behavior of matter. I've written an expression for the de Broglie wavelength here, where you see that it's inversely proportional to mass and temperature. So the more massive the particle, the hotter it is, the shorter the de Broglie wavelength, and sort of the harder it is to have the de Broglie wavelength spread over a large area and see interesting quantum effects of matter. But in making a Bose-Einstein condensate, if you can do just that, make the de Broglie wavelength large, that is, make the volume associated with the de Broglie wavelength bigger than the sort of average volume per particle, V over N, then you can move into a situation where the wave functions of the different atoms overlap with each other. Okay? And now you have this collective system, which in many ways sort of act like a one big atom. And so here, this is a picture from a rather old picture from Gila, CU Boulder, where they take velocity distribution images of a Bose-Einstein condensate. And you see that as they cool the atom sample down more and more, you see a peak right in the middle at zero momentum pop up. And this is the onset of Bose-Einstein condensation, where you have a large occupation of the zero momentum state of these bosons. Now, the Schrodinger equation, the celebrated equation to describe quantum systems, it takes this form. It has a kinetic energy term, it has a potential energy term. These things act on psi, that gives you the energy of the system. For Bose-Einstein condensates, you rather talk about the Gross-Pitevsky equation, which is similar, but you have to add this interaction term, which depends on the density, psi squared, right? This is the density of your atoms. And so it turns out that the density of your atoms, it takes an important part in the evolution of the state of your system. Okay, and I wanted to show you a quick picture from our lab. This is a velocity distribution image of a Bose-Einstein condensate in the temperature range 10 to 100 nanokelvin. So just tiny fraction above absolute zero. Okay, so that's one part. I told you about the Bose-Einstein condensate. Those are the atoms which are going to behave like electrons in our quantum simulator. So in a solid, electrons hop around from site to site. For us, these atoms hop around from site to site in our optical lattice. So let me tell you about the optical lattice. What do I mean by that? Well, first, let's talk about a quick mathematical concept, standing waves. So I can take two waves, two counter-propagating waves, the red and the blue, and I can overlap them to make the black standing wave. In the lab, I can do this experimentally using two lasers, which are two traveling waves of electric field. And if I look at a zoom in the middle, and I look at the time average electric field intensity, I get this pattern. Right? I get a perfectly periodic pattern separated by half of the wavelength of the laser, the laser wavelength, in which I can throw my bosons. So now I have a one-dimensional lattice that I can load atoms into. Okay? And it turns out that we can use multiple pairs of intersecting beams to make two-dimensional or three-dimensional optical lattices. Okay, and so in the experiments that I'm going to describe to you today, that's what we've done. We've used this arrangement of three lasers that are oriented with the relative 120 degrees. And if you look at the potential energy landscape experienced by the atoms where the three lasers overlap, it looks like this, where I've marked the local potential energy minima with the green dots. And so you see that it traces out a honeycomb pattern. So we can make a honeycomb lattice this way. Okay. Now the honeycomb lattice can be spanned or built using a unit cell that has two sites in it. Two of these green dots has a rectangle that sort of wraps around here. And I can translate this rectangle containing these two dots by this vector or this vector, and I can completely build a honeycomb lattice. This will be important for how I tell you about how we do our actual measurements later. But just know that you can span the honeycomb lattice in this way. And so the major point here is that this allows us to create an ultra-cold atom analog of graphene, up to the fact that we're using bosons instead of fermions. Okay, so I mentioned graphene. Let me tell you why graphene is interesting, at least for us, for the upcoming measurements. Well, first, let me remind you that a crystal's band structure and the geometry and topology of state space determines its properties. This is an image of graphene that's single layer, hexagonal arrangement, collection of carbon atoms, right, which has been very celebrated. There's a lot of important physics that's come out of studying this material. These people won the Nobel Prize in 2010 for it. It's discovery and characterization. And the important thing that I want to point out about graphene for the measurements that I'm going to describe to you today is the existence of these Dirac singular points. Okay, you can see the Dirac singular points in this band structure. So this is the band structure of graphene, right? The energy of the electrons versus their momentum in the lattice. You can sort of forget these labels, but know that at this label K, there's a Dirac point where the variation between two adjacent bands grows linearly as you move away from this point. And it turns out that there's something really special that happens at that point. It turns out that these Dirac singular points, they have some important geometric phase that pops up, some Berry phase, where if you are able to move a particle around this Dirac point, sort of regardless of how fast you move the particle around, the wave function of that particle will pick up a pi Berry phase, pi geometric phase. It only cares about the trajectory, not the size, not the time scale. Okay, and that point that a particle can pick up a pi Berry phase is related to some really interesting physics, like Klein tunneling, where electrons can tunnel through very, very large potential energy barriers that you would not expect them to be able to tunnel through, or the half-integer quantum Hall effect. So I didn't mention the quantum Hall effect earlier, but the quantum Hall effect itself is very interesting. Right? People have measured quantized behavior in the conductivity of a material, where jumps in the conductivity are set by fundamental constants. It's the ratio of Planck's constant over the square of the electron charge. And in graphene, specifically because of this pi Berry phase, this pi geometric phase, you can observe a half-integer quantum Hall effect, where the jumps in the conductance is a half-integer multiple of that ratio of fundamental constants. Okay, so I think I've sort of belabored this point. Clearly, graphene is very interesting, and so we want to study it in our cold atom system. But before I move on, the sort of the next level extension of graphene, looking at bilayer graphene, where you take two sheets of graphene, you stack them, and you rotate them. This is also an incredibly interesting system, right? Depending on that angle of rotation, you can have exotic physics pop up, such as superconductivity, right? So there's, and that's also related to this existence of Dirac points, and even these different kinds of band touching points, right? So this Dirac point is a touching point between these two different bands. There's a different kind of band touching point where the variation is quadratic. And so there's so much physics to study there. We want to be able to look at this system with our ultra cold atom quantum simulator. Okay. So before I move on, I want to say that my artificial graphene also has Dirac points and these other kind of band touching points with interesting topological properties. Okay, so I've told you about all the different parts of the quantum simulator. Good, time's okay. I told you about how we build optical lattices, at least conceptually. I told you about the atoms that go into the lattice that sort of behave like the electrons that hop around the solid. This is the experimental apparatus that we use to actually build it, similar in essence to what you find in Kevin Wright's group. Right? So we have generally a light preparation table and a science table. On the light preparation table, there's a bunch of optical components that essentially produce light that we use to manipulate rubidium atoms. Okay, so that is generating laser light that can cool and trap rubidium atoms. And this table just has various components where, say, over here, you do something called absorption spectroscopy, where you measure the difference in energy levels between electronic states and rubidium, and then you use that to lock your laser frequency to that energy difference. And now you have laser light that can resonantly interact with atoms, so you can apply forces to them. And that's how we can sap energy out and so cool atoms. Here's our science table. This is where the magic happens. It's a very sort of cluttered picture. But here in the middle, this is where our Bose-Einstein condensate is. So our experiment starts off with a very hot, sort of 200 Fahrenheit rubidium atoms coming out of an oven. They go down a long tube that does a lot of the initial slowing and cooling of the atoms. There's a chamber back here that you can't see called a magneto-optical trap, where there's another cooling stage done. We use a series of magnetic coils to transfer them into this region here. And then we do a couple evaporation steps. I'm not going to talk about details of that, but at the end, we have a Bose-Einstein condensate in this region. We can send laser beams in from the side. So one comes through here, another one comes through here, another one comes through here. Those are the three to make our optical lattice. So we can load this BEC into the optical lattice, and we can image the system. We do that using this vertical breadboard. We send light from the top down through the Bose-Einstein condensate, and this sort of projects a shadow of the atoms onto a camera where we collect light. And this is how we can do things like the diffraction measurement that I mentioned earlier, or something else called band mapping, which is important for a measurement I'm going to show you, where we can measure the relative proportion of atoms in different energy bands of the honeycomb lattice. Okay, and so let's get into the science part of what I want to talk to you about. Here, I've taken a clip from a recent paper. Please go view this. It's on the archive. It's also under review at Science right now. I'm showing the two-dimensional Brillouin zone map, which you can think of as a way to connect the relationship between the quasi-momentum of the atoms and the different bands that they're in. And so you'll notice that there's a color coordination happening here, and it's an important one for thinking about some of our measurements. So here is a plot of the band structure that I've calculated, showing the first, essentially what I want you to look at is the lowest 4 energy levels, where between the lowest 2 energy levels, you have this Dirac point at K, the linear band touching point, just like in graphene. And then up in the 3rd and 4th energy band, you have a different kind of touching point, a quadratic band touching point, okay? So you see that this lowest energy band is colored in green. You can associate atoms that appear in this region with the first energy band. You see that atoms are the second lowest energy band is blue. When we look at images and you see atoms that appear in this star pattern around the green hexagon, we can know that they came from being in the second energy band of the lattice, okay? And I'll sort of reiterate that. Now, in our measurements, we've done something very different than what cold atom experiments typically do. We're not the first cold atom group to measure Dirac points. However, we're the first to measure it in this way. So what's typically done is a cold atom group will say, make a Bose-Einstein condensate. You can make it 2 spin components, sort of up and down spin. And you can sort of hold one component of your BEC here. You can transport another component of your BEC, loop it around an interesting point, bring the atoms back together and interfere them. And in doing so, you can measure phase differences, like what's done in these 2 experiments from the Block group and the Esslinger group, where they can directly measure the pi-Berry phase that I mentioned, this geometric phase that your particles pick up when you do loops around the Dirac point. Okay, that's exactly what this shows here. So for a loop around the Dirac point, the phase picked up by their atoms, you see acquires this jump of pi, right? A rather sharp jump of pi. Or in this experiment, where they actually have the ability to tune between the equivalent of 2 different solid state materials, either graphene, where, I mentioned in graphene, there's 2 sites in the unit cell. The particles would experience sort of equal confinement to these different points. You can imbalance the confinement to those different points, and then your system looks more like hexagonal boron nitride, where the touching point at K, the Dirac point, sort of disappears. And they see this in this measurement, where when the 2 sites of the unit cell are balanced, this is this case, where there's this touching here, this is the Dirac point. When they do a loop around the Dirac point, their system picks up this pi-Berry phase that you see on this, this horizontal axis here, right? Okay. Alternatively, cold atom systems can also sort of directly measure that there's some interesting Berry curvature or Berry phase associated with that Berry curvature. So they can do complete quantum state tomography, that is, measure the amplitude and phase of the Bloch states in the Brillouin zone. And that's exactly what this is, where these red and blue measurements are showing a direct measurement of the Berry curvature, where you can see that there has to be some Berry phase that will be confined to these points. These are the Dirac points, right? Okay. And so, again, I want to emphasize that you're not doing some sort of loops around these singular points, these Dirac points. We're doing something very different, right? We are going to evolve our atoms directly through the touching points, and then we're going to turn at some angle, okay? So it might sound like a small difference, but it's not. It's a completely different measurement. It's not an interference measurement at all. It's actually a measurement of this quantity called quantum distance. And I'm gonna argue a little bit later that this distinction is important because it allows us to do a measurement that other cold atom groups that only do interferometric measurements can't do. Okay, but for now, how do we do quantum distance measurements? How do we evolve our atoms through these singular touching points and through these Dirac points? We do it by translating our lattice. And it turns out that if we can translate our lattice, then in the lattice frame, the atoms are moving. And so we can give the atoms some momentum. Okay, so I mentioned that we translate our lattice. We have these 2 experimental knobs, F12 and F23. These are some time-dependent parameters we can control in the lab, multiplied by A12 and A23. These are those lattice vectors that I showed you in the picture of my honeycomb lattice, right? So I can give my lattice, my optical lattice, some arbitrary velocity in 2 dimensions using some experimental control parameters. And it turns out that the relationship between the lattice velocity and the momentum of my particles in the lattice is given by this expression here, where the momentum of the particles in the lattice is the lattice velocity multiplied by minus the single particle mass. Right? So what this means is that I can give my particles an arbitrary quasi-momentum, momentum in the lattice in 2 dimensions. And so I can explore all of this region here. And so just to sort of show that we can indeed do this, I have some diffraction images here for you to look at. So we can make predictions for what these diffraction images should look like. This is an image of loading the atoms into the lattice and then shutting off the lattice. What this does is it takes a Bloch state from the lattice, that psi I showed you earlier, and it projects it onto plane wave states. So this is a measurement of us taking a Bloch state and then seeing how you can write it as a sum of different e to the I kx. Right? That's why you see these different peaks here. So I can predict that if I just turn on the lattice and I don't translate it, I should see a pattern in this diffraction image that looks like this. And indeed, in an experiment, this is what I see. Or I can use this technique to give my atoms some quasi-momentum that takes them from gamma here, this is zero quasi-momentum, moves them over into this region. And theory would suggest that this diffraction image should look this way, and I indeed see something very similar. Right, so, yes.
So I have a short question.
Sure.
How many atoms in the whole are you using to produce this pattern? The other question is this a genuine 1D layer or is it several atoms there?
It's the lattice of tubes, and we use 30 to 50,000 atoms. I think in the measurements that I'm going to show you later, most of them were done with 10,000 atoms, maybe a little bit less. We were having some interaction effects that were kind of messing things up. So we wanted to lower the number of atoms as much as possible. But
So you said the first one, so you actually confine,
so there's not much vertical confinement transverse to the lattice plane direction. So essentially, we have a hexagonal arrangement of these tubes that extend vertically in the transverse direction to the lattice. Okay, and so let me tell you about our first probe using this quantum distance measurement of a Dirac point. First, let me point your eyes to A here. So this is a little clip of my Crystallin zone. I start my atoms at gamma, that's in the center of this green hexagon at 0 quasi-momentum. And I evolve their quasi-momentum to this point here. This is K, this is where the Dirac points are. And this is where something really interesting happens. This is where the wave function that describes the atoms becomes ill-defined. I move the atoms into this point and then I turn at some angle. That's what I'm showing here in this magnified image. Again, I'm going from gamma down here over to the Dirac point and I turn at some angle theta. And I'm going to do that same kind of measurement where I look at images of the atoms after I've turned through a series of different theta where my atoms end up on this circle, some radius away from the Dirac point. That radius is 0.4 times the distance between 0 momentum where the atoms start and the Dirac point. Okay, so again, I can sort of touch the Dirac point, go off at some angle. I can take one of these band mapping images of the atoms, and I can do that around this whole circle. I've shown some representative images of doing exactly that here. Here for theta equals 0. So this is going into the Dirac point and turning around and then measuring the relative proportion of atoms in the different bands. I see that most of the atoms, by looking at this density plot, red corresponds to where most of the atoms are. They fall into this first hexagon. Right? This is associated with the first, this is the first Brillouin zone associated with the first band. So by looking at this image for theta equals 0, I know that most of the atoms are in the first band relative to being in the second or third band. If I look at theta equals pi over 2, I see that sort of half of the atoms are in this central hexagon. So sort of half of the atoms are in the first band, and sort of half of the atoms are in the second band because they're in this star pattern in the blue regions that are around the central hexagon, and so on. And so I mentioned I can do this for various theta, and I can measure the relative proportion of atoms in the different bands. That's what this plot is. So the green data are measurements of the proportion of atoms in the first band versus the blue being in the second band. And what we see is for sort of a wrap around the Dirac point from 0 to 2 pi, we see one full oscillation of the band population. So for theta equals 0, the atoms mostly stay in the first band. And by the time we go fully around and we get back to theta equals 2 pi, the atoms are mostly in the first band. Compared to a situation where we turn, or we go straight through the Dirac point, that is theta equals pi, and there's a large population inversion where atoms go from mostly in the first band to mostly in the second band, right? Okay, so why is this interesting? This is telling you that there's something special happening at the Dirac point. This is a two-band system, a sort of two-state system. So you can map this onto the behavior of a pseudo-spin 1/2 in a magnetic field, okay? And when I do that, the picture is, it looks sort of simple. It looks like there's an effective magnetic field that wraps around the Dirac point, K, that grows in magnitude linearly as you move away from K. And so one way to think about this experiment in this pseudo-spin picture is, say I come along this ray, coming from gamma into the Dirac point, you can call the state of my system spin down. And as long as I stay on the ray, the state doesn't change. But as soon as I cross the Dirac point, all of a sudden, what was spin down, the state that was once spin down is now in an effective magnetic field that is misaligned with it. And so that state is really in a superposition of what is now up and down. That's the up and down states defined by the direction of the applied magnetic field, right? Okay, and so I already mentioned this two-band model. I haven't mentioned that these population dynamics, this sort of oscillation, is completely, okay, I should be more careful about this language, but this is time independent, right? We've tested this for several different times, and you don't see a deviation in this behavior until you are not respecting time scales set by band gaps, right? But we see that the fact that the atoms are changing proportion in these different bands, it is set by this quantity here. So I mentioned the Berry connection earlier. I mentioned that this is important for describing these other properties of solids. Cold atom experiments typically measure the diagonal elements of this Berry connection. We are sensitive to the off-diagonal elements. These are what produce these non-abelian state rotations that are time independent. Okay. This gives us a measurement of quantum distance, what I'm calling d squared here, which is defined as 1 minus it's the square of the overlap between the two functions u that appeared in my block function, the two cell periodic parts that describe how the wave functions look in the lattice. Right, but I can define this object called quantum distance. I've measured directly this. This is a measurement of quantum distance. And it turns out that the quantum distance is important for measuring properties of materials. Right, we have many examples of how the Berry phase is important for measuring properties of materials, or for describing properties of materials, not measuring. There's this other term, the quantum distance, which I've measured here, which is also important. And so I'll give you one example of how it's important. This is rather technical, but there's this interesting paper that came out in Nature last year, I believe, that showed how in a system that has band structure, where you have a flat energy band that touches one that has a quadratic energy dispersion, and at that touching point, the wave function is ill-defined, just like in my system, that you can have these energy levels that split. What once was a highly degenerate energy level can split, and the spacing between these levels are set by this parameter, quantum distance. Right, and it turns into several measurable properties of the system. Okay, so I just want to say that people have sort of known for a while that quantum distance is important, but I think the extent to which it is important is sort of only now really starting to be appreciated. And so, final comment about this is the metric tensor. So it turns out that the Berry phase and the quantum distance combine to form this tensor called the metric tensor, which you can define in this way. It's this Gij. And so just like how a relativist might write down a metric tensor to define distance in space-time, you can use a measurement like this, and a measurement of Berry phase, to write down a quantum metric tensor that defines distance in the state space where your wave functions live. And it turns out that that distance matters in terms of describing properties of your system. Okay. So we started 10 minutes late. Am I okay with another 5 minutes or so?
Well, it's only 4:05 right now, so you have until 4. Oh, I guess we usually do 10 minutes question. I think so 4 minutes.
Great. Okay. I'll sort of be quick about this because this is actually, I have something even more exciting to tell you about. But I mentioned adiabaticity. I mentioned that what I showed you in the previous slide is time independent. It's a geometric thing. It's a topological thing. Now, it does turn out, though, that the Dirac points, they do have a sort of effective size. And the question is, how do we know that? Well, we can measure it by having the atoms undergo trajectories that look like this. So again, this is my Brillouin zone. I've zoomed in on it. The atoms start here at gamma, and I can evolve their quasi-momentum, their momentum in the lattice, along different trajectories that say go from gamma to this Dirac point, and then to this gamma point, or from gamma to this point, separated some distance from the Dirac point, and et cetera. I can send them through all of these different trajectories, and I can do so over different time scales. And then I can measure the proportion of atoms, say, in the lowest energy band or the next highest energy band. And I can plot that proportion versus the trajectory that I've evolved the atoms along. All right, that's what this plot is. And so as the data becomes more red, so near the top, I've undergone one of these trajectories more slowly versus the blue, where I've gone through the trajectory more quickly. And so let me highlight this point M, right? So M is sort of maximally far from both the rack points here and here, right? So if I go from gamma to M to gamma, this midpoint here is sort of maximally far from the two Dirac points on the side. And so I can see this really clear time dependence there, right? If I look along this vertical slice, I see that as I go more slowly and slowly, so I go from the blue to this sort of purplish region and up, the proportion of atoms that stay in the lowest energy band grows. This is sort of what you expect from Landau's inner physics when you're evolving your system near some band, avoided crossing between different energy levels, okay? So this shows time dependence, right? As I, again, as I go along this trajectory, gamma M to gamma, more slowly, I see more atoms stay in the ground band. However, if I look at the same measurement around the K point, around the Dirac point, say here, you see that sort of up to the size of my error bars, nearly independent of the time, I always see the same proportion of atoms in the lower span, right? Okay, and so I can use this, I can use a threshold. This threshold I'm just saying is 0.5 to define an effective size, where I can see at what distance away from the Dirac point, the population of atoms, say in the first band, equals half. And I can plot that as a function of time, and that's what this inset is. And so I see that as I evolve my atoms more and more slowly through the Dirac point, or near the Dirac point, not through the Dirac point, near the Dirac point, the effective size R looks smaller. And this sort of makes sense. Why? Because I always have to think about the band gaps, the local band gaps by some point, right? So there's some energy gap that defines a time scale. If I evolve my atoms faster than that time scale set by the energy gap, then the bands effectively look degenerate. And if they're touching, it looks like a Dirac point again. And so there's a region, depending on how fast I'm evolving, over which it looks like this band touching point has grown in size. And that's what this measurement is of. Okay, this is my last data slide. And this is the really special thing. This is the thing that cold atom experiments before that use interferometry can't measure. So here, this is a quantum distance measurement of a quadratic band touching point where, unlike a Dirac point, which has a pi Berry phase for a loop around it, a quadratic band touching point has a 2 pi Berry phase. And if you do an interferometric measurement, you can't distinguish 0 from 2 pi. And so if this point is topologically non-trivial, you wouldn't be able to see it with an interferometric measurement. However, with a quantum distance measurement, where you go through that singular point, you touch it and you turn at some angle, you can see it. You can see whether or not this is an interesting point. And that's exactly what we've done. So doing the same sort of experiment, I can talk about a detail of how we do this later, but we load our atoms to the third energy band. We come back to gamma, and then we turn at some angle theta for multiple points around gamma. We do band mapping images again. We overlay the hexagon. We see what the relative proportion of atoms are, and we plot them here. And so what you can see is that if you look at the relative proportion between atoms in the third band in the red and the fourth band in the purple, for one revolution around the gamma point, the quadratic band touching point, you see 2 oscillations in the band population. Right? This is reflective of that 2 pi Berry phase. This is a measurement of the fact that there is a topological winding number of 2 for this point instead of 1 for the Dirac point. And again, this is really special because up to now, cold atom experiments haven't been able to measure it. And there's a whole host of interesting condensed matter physics to study for systems that have a quadratic band touching point. Okay, and so that's the last sort of bit of data I wanted to show you. And so I will conclude here. My conclusion is this. An ultra cold atom quantum simulator is a powerful tool that allows for the simulation of real materials or toy Hamiltonians. Okay? Measurements of quantum distance allow the non-trivial topology of Dirac points and, importantly, quadratic band touching points to be directly revealed, which is what I've shown you. And more specifically, we observed a quantized winding number of 1 around the Dirac point. This is sort of what you expect. This is associated with that pi Berry phase, and 2 for the quadratic band touching point. There's a whole host of interesting work to move on to in the future. You know, we're mostly a Kagome lattice experiment. The Kagome lattice is interesting because if you look at that band structure that I showed for the Kagome lattice, there's a flat energy band. There's lots of interesting physics to study with flat energy bands. And that leads us to this question of where do bosons condense? Right? You tend to think of bosons condensing in the lowest energy level, but what if your energy levels are flat? Where do bosons condense? We want to study that question. We can actually address that question in the honeycomb lattice. And so that's the direction we're moving on to. But I really wanted to show you this interesting picture. I can't tell you any interesting physics about this because I don't understand it yet, but we've sort of moved on to a new project where we're studying the quadratic band touching point. We've evolved our atoms to the quadratic band touching point, and we've held them there for some time. And after some time, you hold them there longer and longer, you see the star pattern appear, where the atoms are for whatever reason, sort of aligning themselves along the Brillouin zone edges between the 3rd and 4th energy bands. And so I just kind of wanted to get you interested here. But thank you for your attention.
Let's just take this here. Thank you very much. I know we've gone beyond the usual time, but let's take a minute or two for maybe some quick questions. We will always, as usual, have time after the talk for extended discussion with the speaker. Miles, your hand went up first.
Phonon modes? I don't think so with static lattice system, just because a phonon in a standing wave lattice like this, it would mean that you have I think a modulation that sort of sweeps through the potential energy minima defined by the local minima of the lattice. Maybe if you have some sort of tweezer array, maybe you can do something like this, but I think if you have a system where you're overlapping lasers to produce the lattice, I'm not sure that you could make for phonons in here.
So when this analog graphene, the particles are still bosons and not protons.
They are.
So there's no way to actually truly create an analog graphene with fermionic excitations. The reason why I ask that is sometimes, so people like Andy Lucas have suggested that near the Dirac point, you're going to have a strongly coupled quantum plasma. So I was wondering if there's a way to actually see this physics in an ultra-cold atomic setting.
Maybe. So yeah, I think Tillman Esslinger's group, he studies fermions and hexagonal lattices. There's a ton of interesting physics there. That's certainly an important step towards making a system that's more like graphene. So I see this as an analog of graphene in the sense that if I look at the band structure, I have these interesting topological properties that I want to study. But if I want to make a more faithful representation of solid state graphene using this quantum simulator, then yeah, I should have 1 fermions instead of bosons, and also have some sort of long range interactions. Right. So in my system, I essentially just have energy associated with scattering at the same lattice site, but electrons are charged. They have a Coulomb interaction that extends over the lattice, and so I should have some long range interactions. And I think people are probably going to move there sometime.
Thank you.
Okay. I guess if there's one more burning question, go for it. No, if it's quick, sure, let's make this the last one.
Thank you for a wonderful talk. How easy or hard is it to change your lattice shape? And have you thought about doing in the near future lattice to look different than this particular graph?
Yeah, that's an interesting question. It depends on how you want to change it. So I can sort of easily stretch the lattice by just imbalancing the beam power. So I showed that there are 3 lattice beams to produce this hexagon. If I make one of them strong relative to another, then I can sort of stretch the lattice along that direction. So I can do that. I can shrink or I can magnify sort of positively or negatively the lattice by changing the wavelength of the laser. But that's about it. If I want to say move from like really different geometry. So in my opinion, I would say a different geometry is one that has a different rotational symmetry, like switching from triangle to square. You can't do that with this system. You would have to physically move your optics to produce a different lattice. But with something like a digital micromirror device or something, you can maybe rapidly switch between triangle and square or other geometries.
Okay, well, let's thank the speaker, and anybody more burning questions? Thanks for coming again, everybody. It's really great to have everybody back in this room again, seriously. Yeah.